Hello everybody. I just wanted to thank everybody for attending the first webinar. There's more to come, rest assured. And the other thing I wanted to point out is that there were many questions that were asked during the seminar. And so what I'm going to do is come back to my YouTube channel, and there's going to be a Q&A. I'll read up all the questions, and answer all the questions. I thought it'd be easier to do verbally than via email. And the other piece is there's going to be part 2 to this webinar on my YouTube channel. Reason being, we had originally wanted an hour and a half, but the invite went out with 1 hour, and I was respectful of those who made time for the 1 hour webinar. So I didn't want to extend the webinar by 30 minutes. So what you're going to see is a part 1, if you will, where I'll go into some of the packet traces a little bit more detailed, a little bit more thoroughly. And also I'll show you the transaction expert that I showed at the end of the first video, a little bit more detail. Okay, with that, I hope you enjoy it, and I look forward to seeing you guys on part 2 coming up soon.
Thanks for attending the first of this 3-part series in the packet trenches, a time-tested approach to packet analysis and troubleshooting, authored and presented by Hansang, Riverbed's Chief Technology Officer and seasoned practitioner of and vocal evangelist for the art of packet analysis. I'm Janice Vampanato, Business Development Manager for Riverbed's Performance Platform Technology and the coordinator for this Riverbed Packet Center of Excellence training event. Now, a couple of things before I hand it over to Hansang. Note, if you didn't get the message from the email that was sent, this is a progressive training in troubleshooting methodology. So it's scheduled for presentation over the course of the first 3 quarters of this year. Obviously, the first one is taking place today. The second one will be on May 12th, and the third and final on August 18th. Those are the live events. So if you want to mark your calendars, that's May 12th and August 18th for the next 2 segments. And registration invitations for those 2 remaining events will be sent about 2 weeks or so before their delivery dates. So if you don't write it down, you'll be getting an email just to tell you when they're happening. Note too that these 3 sessions are comprised, these 3 sessions, the first today, are comprised of content from the first 3 chapters of Hansang's Art of Packet Analysis book. And the recordings of each one of these live events will be released post-event on Hansang's YouTube channel, on Wireshark.org, and probably some other sites. Then, after these first 3 sessions, the remaining chapters of Hansang's self-published book will be posted on his YouTube channel as well. So after August, when we've gotten through the first 3 chapters progressively, or as much of them as Hansang is able to fit in this time, then the remaining chapters will be published so that you can continue with your education. And information on the location of the recording of this live event will be sent to you all in email within a few days after we're through here today. And another note, if you like this webinar, you might also enjoy and gain a lot by attending SharkFest, which is the annual Wireshark Developer and User Educational Conference that includes 20 and more, we're still adding to the lineup, expert instructors, including Hansang, Laura Chappell, Jasper Bongeritz, if you're familiar with Jasper, Betty Du Bois, Kristen Landstrom, Chris Greer, who is on the phone with us today, Phil Shade, and some others. SharkFest is taking place in 2 locations this year. We're starting one in Europe for the first time. But the one in the U.S. will be at the Computer History Museum from June 13th to 16th. And the one in the Netherlands, our first in Europe again, will be October 17th through the 19th. And information on SharkFest and how you can find out more about it will be included in the post-event email as well that you'll get. Now, back to the webinar today. If you have questions you'd like to pose during the course of this presentation, please type them in the chat window, and I'll be prioritizing them so that Hansang at the end of the session can read some of the ones that seem to have the most general application aloud and answer them. Again, as many as we can, given the time allotted at the end. Now, any questions that aren't addressed, don't feel neglected. We'll get back to you individually after the event by email. And for those who will be watching a replay of this live event and would like to pose questions, please send them to sharkfest@riverbed.com, and they'll be routed to Hansang, whoever needs to answer them, and we'll get back to you. Again, that's sharkfest@riverbed.com. Okay, so that's enough. We'll get on to the main event now, and thank you again for your time and attention. Please take it away, Hansang.
Thank you, Janice. Okay, so I wanted to announce today's big news of NASA finding gravitational waves, but they scooped me. And for those of you that don't know, happened about an hour and a half ago. Check it out. I'm told that it's earth-shattering discovery. We'll see about that. But today's presentation is a little bit more grounded, and it's really a passion of mine. And it's interesting because there are folks on the call that I recognize from many, many years ago, one of which is Randy Ritchie from Base 2 Solutions. And the reason why I bring him up is because many, many moons ago, Randy gave me an opportunity to play with what was then called the sniffer. And I'm talking about the Network General sniffer. So from a timeline perspective, that was a long time ago. I've been hooked ever since. And today we have Wireshark. So, a tremendous shout out to Gerald, who actually wrote Wireshark, and as he likes to call it, it was a weekend project that got away from him, and now we have the world's de facto standard in packet analysis. Okay, so, just a quick way, I wanted to give a synopsis of why this event is occurring. As you might have seen my LinkedIn post, I started to write a book. In fact, I got through the first 3 chapters. And it occurred to me that it was more for my benefit of having a book published than anything else. And quite frankly, packet analysis is a very multimedia experience, right? You have to see the packets in Wireshark doing all the analysis. And so I thought, you know what, book is great, but maybe a multimedia format like this is better. Okay, so here we are today. And I wanted to go over the agenda. These are the chapters of my book. And so the first part, which we'll go over today, and if it runs over, we'll continue on. If you watch the first 3 sessions that Janice mentioned, you'll be caught up. And then I'll start publishing on YouTube more regularly on my channel that you see in the bottom of the screen there. The first part is, there's some theoretical TCP IP. I'm not going to cover that. I'm actually going to cover from a troubleshooter's perspective what's important and why it's important. So the first 15, 20, 30 minutes of this, we're not even going to open up Wireshark. And you may think, oh man, where's Wireshark? I want to go right straight to Wireshark, and that's great. But these are fundamental concepts that you must understand if you want to call yourself a protocol analyst. Okay. Number 2, chapter 2. We may skip over and go to chapter 3 in the next session. It's called the mise en place of Wireshark. What's mise en place? For those of you that read Anthony Bourdain's book, it's the French term for chefs who like to have all their ingredients, knives and whatnot, in a common location. So every time they get to the restaurant, they set it out so they can be very, very efficient in getting your orders out to the table. Wireshark works exactly the same way. You have to have a common framework that works for you, and you have to use it the same way to speed up your analysis and, more importantly, to identify anomalies. Okay? And if your Wireshark is set up in such a way, I can guarantee you that you're going to be able to spot anomalies and make you go, I wonder what that's about, and more often than not, find root cause. Number 3, this is a lesson that a lot of us learn through the School of Hard Knocks. You think you're onto something, you start telling people what to do, why it's wrong, and it turns out with just a little bit more digging, you would have found the real root cause. Okay? And packets don't lie. It's all in there. It's just a matter of how many layers you want to peel. And more apropos to this session and future session is, do you have the understanding to know what layers to peel off? Okay? I keep coming back to this, but it's fundamental to protocol analysis. Packet analysis, it's not something that you just pick up overnight. It's more art than science, but it certainly helps to read up on, you know, the Comers of the world and Stevens of the world, and of course the RFCs to get a true understanding. Number 4, a little cheeky. I'm sure a lot of you network infrastructure folks out there have said this, uttered this phrase many, many times. It's not the network, but how do you prove it? How do you prove it so that you can go on to finding the real root cause? And that's what number 4 is about. It's not deflecting blame or throwing it over the fence. It's about, let's get to the real root cause, but you still need to have mean time to innocence. Okay? Large enterprise, number 5. There are some things that you only see in a very large enterprise. So again, we'll talk about all the complexities that come with the size. Okay? Classification of common issues. This is pretty interesting because you can quickly triage what class of problems, and honestly, there aren't that many. Okay, and you'll see some of it today. And so this is a way of bucketizing and triaging it so that you can quickly either get it to the right people. You know, some of the more common problems can go to the junior engineers. Some of the more esoteric ones you can kind of keep for yourself, etc. Okay. The burden of running a financial network. This is very specific to financials because I come from financials. I spent 13 wonderful years at Citigroup, and I learned a lot. Incredible place. And so I wanted to talk about some of the unique requirements of running a financial network and how it differs from regular networks. Okay. Number 8. So I'm sure a lot of you are running through this now. How do you do a data center migration? Where do you start? I can tell you that over the course of many, many years at Citi, there were many, many data center consolidations for various business reasons, technology reasons. And so here, you know, it's data center migration, not migraines, right? I want to help you understand these concepts so that you don't have what's called a self-correcting mistake. What's a self-correcting mistake? You make it once, you get fired, you're not going to make it again. Okay? So we don't want that to happen, so we'll talk about that. So how long will all of this take? I'm not sure, because sometimes what I don't want to do is hurry up and gloss over things because I believe these are very fundamental concepts. And quite frankly, after the first 3 sessions are over, I'll be more regularly publishing on YouTube. And it's your time. You can watch it at your leisure, and I won't make it so that it's 2-3 hours long, okay? Because it's hard to consume some of this information. All right, so without further ado, let's move on to a topic that's near and dear, and that's, of course, TCP and round-trip times. So why is this so important? It's important because you need to understand, and it's a common mistake that rookies make. And someone had asked me on YouTube channel, in fact, recently, why some of the Wireshark views that I was showing didn't make any sense. And it didn't make any sense because you have to, when you're doing TCP analysis, you have to keep track of where you're capturing the packet and where in the network, where it's flying around, okay? And you have to do that because the conversations and stitching the conversation together won't make any sense unless you're spatially aware. Okay? A problem that presents itself from the client-side capture can and will look different from a server-side capture. Okay? It's great if you can capture on both sides, but more often than not, you can get by with just capturing on one side. So, one of the fundamental rules of TCP, this is something that you need to understand and tattoo on your forehead. Okay, it's that important. This is, and the reason why this is important is because this happens quite a bit, and it's very, very easy to fix. And you can look like a hero. Okay, so one of my jobs is to be a hero maker of all of you guys so that you can go and show off to your bosses. Okay, so the first sentence there, you can never transfer more than one full window size per round trip. A lot of you probably have read this in various books, textbooks, online, etc. And you have to really think this through. Why is it that you can never transfer more than one full window size per round trip? Okay? So I wanted to give you an example. Here we have a very small window size of 8760 bytes. This is a TCP window size, and it's the receiver's window size. This window size that you see in Wireshark is only the receiver's amount of bytes that the receiver can handle. Okay? Unfortunately, there is no sender's window size, but we'll talk about that in just a second, how you can empirically gather that. So, in my example, I have an impossibly long round trip time of 1 second. In typically 1 second, you can almost go around the globe 4 times, right? Because as network engineers, we work in milliseconds, not in 1 second, etc. So, 1 second round trip time, so one-way latency is a half a second. From point A, which is the starting point here, this is the client side, the server is sitting over here on the right, it takes a half a second for these packets to fly over to the other side and half a second to fly back this way. But there's another rule, and it says once you've exhausted your window size, you can't transmit. Okay? And why is that? Why is it that TCP says once you've exhausted your window size, you cannot transmit? And it's for this reason. One of the fundamental tenets of TCP is it guarantees delivery. And there are others, stream-oriented, there's end-to-end flow control, etc. But the one that we care about is guaranteed delivery. So how many of you guys thought about how that really works? We've all read it from textbooks. We've all read it from online websites and other webinars. TCP's difference between UDP is that it guarantees delivery. How does it do that? Because when TCP gets a chunk of data from the application, let's say it's a Word document that's being saved over the network. If a amount of data, a packet with data in it gets lost, TCP cannot go back to Word and say, I'm sorry I lost page 6, can you send that back to me? It doesn't work that way. So what TCP does is it sets aside a buffer space. In this case, we'll call it 8760 because that's my example. And think of this as a warehouse full of shelves. Okay? And each bin can hold, in this case, 1460 bytes of data. So when TCP transmits these 6 packets here, each containing 1460 bytes worth of data, it makes a Xerox copy and puts it into that warehouse shelf. It does this because if these packets go missing along the way, TCP, without bothering the application, can go back to the warehouse, look at the particular shelf with a particular sequence number, meaning amount of bytes that was transmitted, amount of bytes that were lost, and make another Xerox copy and put it out onto the wire. And once it gets positive feedback saying, I've received this many bytes, it can clear that shelf, make room for it, make a new Xerox copies of the application, and send it on its way. Okay? So what happens when this warehouse gets full? You've run out of bins and shelves to make a Xerox copy of the data that you, as TCP, need to transmit. In that case, TCP has to do what? TCP has to shut up. TCP has to stop transmitting because he can no longer guarantee delivery because he's run out of room in the buffer, okay, in the warehouse, the shelf space, to guarantee that he can go back and recover and re-Xerox those files and put it back on the wire. Okay? So hopefully that made sense, but let's see it in action. I spent some time. I'm not a PowerPoint animator by any means, but this is what I'm going to show you right now. I have a receive window size of 8760. So the receiver on the right-hand side will receive up to 8,760 bytes. For now, we'll say that the sender has the same buffer space, 8760. Okay? So he has, in his warehouse, room to store 8,760 bytes worth of data. Remember, each one of these packets, as they go out, are being Xeroxed and put into shelves in a warehouse that can hold up to 8,760 bytes. So let's see what happens. The packets train starts to leave the train. Okay? And I spent a lot of time on that animation, so I hope you've enjoyed it. And the idea is, on the right-hand side, okay, this is where the receiver's network card is. And we see here that the first packet, worth 1460 bytes of data, is starting to enter the network card. But over here on the left, you see empty space. Why? Because once he's sent 8,760 bytes, which is all encapsulated in these 6 packets, he's out of shelf space. TCP has to stop. So we now have dead space from here, the client, to the trailing packet that you see here. Okay? This is dead space. Nothing's happening right now. And of course, we know that the rule of TCP says that once you receive either 2 packets or 2 full-size packets, 2 full MSS-size packets, you need to acknowledge. And we'll talk about in later sessions why the distinction between 2 full MSS packets or just any old 2 packets. So once these 2 packets show up, what happens? The acknowledgement goes to the other side. So how much time has elapsed here? Okay, let's think about this. When the first 6 of these packets flew from left to right, it was a half a second. And it takes the acknowledgement about a half a second to come back to here. Once the sender receives this acknowledgement, he can clear out the first 2 bins in his shelf, because the acknowledgement came right from right here saying, I got the first 1460 bytes, I got the second 1460 bytes worth of data. That's positive acknowledgement. I can clear out this bin in my shelf space here and transmit 2 more. And this cycle will repeat again and again and again and again. And this is the reason why you cannot transfer more than 1 window size, 1 full window size per round trip. Okay? Now hopefully that made sense. If not, when the session is published, watch it again and go through some of my other sessions from my past SharkFest sessions, because this is very easy fix. This is very easy to identify, and this is very easy fix. It's an easy fix because the application developers don't have to get involved. Okay? If the application is willing to give us a lot of data to TCP, all you have to do is increase the TCP window size. In fact, TCP has gotten smarter over time. Already, we're seeing auto-tuning TCP window size. Okay? Auto-tuning means that TCP will increase as needed and throttle back when it hits a bottleneck. So while this is not as big of a problem as it was maybe 5 years ago, I can tell you from experience that there are a boatload of applications that fall into this category. Okay? Think about how many Windows servers and clients that are out there that are not up to the latest version. Okay? It's too many to count. So, what do we do about this? As a network guy, helping out the business, helping out the application team, how do you solve this, and what's the best number? How do you derive the best TCP window size to maximize the throughput? And there's a rule. Okay? Because in this example, look at the horrible throughput for this example. That's 70 kilobits per second. Okay, I could have done that with a modem 15 years ago. So clearly, this is not a high throughput application. And the limitation is the TCP window size. So there's a rule, okay? It says, if you want to beat this maximum throughput, there's a thing called bandwidth delay product. Okay? All bandwidth delay product says is, I'll show you that in a second, it will give you the TCP window size that will maximize and fill the pipe in TCP world. Think about what I just said. TCP will fill the pipe. So you have to think to yourself, is this the only application that's running on your network? Probably not. Do you really want to give this one application 100% of the bandwidth? Probably not. Okay, so this is where the art of packet analysis comes in. Mathematically, I can give you a number, TCP window size, that will guarantee 100% utilization. In reality, that's not how it really works. Okay, so these are approximations, best effort, best practices. So let's go through one as an example. We have a realistic scenario, probably from New York to Singapore, and it's about round-trip latency of 250 milliseconds. And a bandwidth, it's only 45 megabits. So maybe this was very common, I don't know, 5, 6, 7 years ago. Okay, having a 45 megabit internationally was pretty common, and this was a very common size, maybe even longer than that, maybe 8 years ago. Regardless, it's just an example. So the bandwidth delay product, all that says is you take the bandwidth, the minimum bandwidth between site A and site B, and multiply it by the delay. Okay, that's why it's called bandwidth delay product. You multiply the two. So 45 megabits per second, multiply that by 0.250 seconds, and you get 11.25 megabits per second, or 1.4 about megabytes. If you make your TCP window size to be 1.4 megabytes, theoretically, you're guaranteed to fill that pipe. You will have a streaming service that's guaranteed to have 45 megabits at all times. TCP and TCP's window size will not be the bottleneck. Okay? So, I said here earlier, and you can see here, bandwidth delay product in theory gives you the ideal window size to fill the pipe. Or does it? Okay? Things in protocol analysis is interesting, and maybe in technology in general. It's not always black and white. Mathematically, it is black and white. But in the real world, this isn't how it works. And oftentimes, you're going to hear someone say, you know what, just double the bandwidth delay product. And when I first heard this, I said, hold on a second. Why do I need to double this? Okay? And those of you that attended my SharkFest session know that to become a protocol analyst, to become really, really good at packet analysis, you have to be that annoying 4-year-old, okay, that have to question everything. Don't take it as gospel. Get to a point where you truly understand the technology and the protocol that you can answer unequivocally why bandwidth delay product in itself theoretically is a maximum value, but in reality it's not. Okay, so I'm going to give you an example of why that is. And I just got a quick hit on the, it's very apropos here, is the auto-tuning TCP window size the same as a sliding window size? Yes and no. I say yes because the auto-tuning TCP window size, Michael, gives you the big window size you need to achieve throughput. The sliding window comes in. So think of this way. The sliding window is how fast you can clear out the shelf in your storage. The faster you can clear it out, the more room you can have to Xerox the data for guaranteed delivery. And so it, of course, increases your throughput. It goes hand in hand. Okay? So the first part of auto-tuning is just make the TCP window size bigger. In terms of sliding window, it comes into play because you saw in my earlier demonstration, you need to clear out these shelf space as quickly as possible. Okay? And getting back to this session, this is the ideal window size, 1.4 megabytes. So let's understand why, in fact, it's often the case that you will not get the maximum throughput. First, look at this diagram that I drew out. It's not animated because it's too much of a pain in the ass, so I didn't animate this one. But the the message here is clear. These packets have left the station. We typically call them packet trains. And they left the station, all serially. And here's the first packet, second, third, etc. I drew this on purpose. Notice this space and separation between packets. Okay? What causes these delays? Why is this first packet neck and neck, the ending and the beginning is right together? Here there's a little bit of overlap as if this packet kind of overtook the second packet. Here's this poor fourth packet here that's a straggler, and it's got a lot of dead space between the two. The reason why this happens is a couple of reasons. Number one, there can be a serialization delay, okay, meaning there's a big truck ahead of you. You have to wait your turn to get on the highway. As simple as that. Okay? It's called congestion. The more people that are trying to get on the highway, the more congested it gets. And those of you that live in LA or Orange County like Randy, and Chicago and New Yorks of the world, we all know this and feel this on a day-to-day commute. When there's more cars on the highway, not yours, other people's cars, it causes congestion. So packets tend to bunch up or spread themselves out. That's the easy explanation. There's another reason why having a bandwidth delay product alone doesn't give you the guaranteed bandwidth. And that's because how are these packets transmitted on the internet, on your enterprise? Okay? We have things like switches and routers. And what do switches and routers, what do? They take these packetized Ethernet frames and put it onto the wire to the next hop, etc. And every one of these devices have buffers, their own buffers to handle an onslaught of traffic. Okay? And if you had a transfer with just a single cable from client to server, yes, the 1.4 megabyte window size here will guarantee delivery and filling of the pipe. But if every step of the way you have someone that can queue up X number of packets or X amount of bytes of data, you've essentially increased that buffer size from end to end. Okay? You've essentially increased the bandwidth because they can hold on to the packets a little longer and a little more and then transmit them out. And this is the reason why heuristics tells us that if you want true wire rate throughput, double the bandwidth delay product. Okay? It's all because of overcoming serialization congestion, and more importantly, and more to the point, all these buffers that are along the network. So, I'm sure most of you who've dealt with routers in the past, and I'm assuming that's 80 to 90% of you in the listening in, had to tune the buffers on your routers. Okay? And just know that when you do that, the unintended consequence is you may not be dropping frames anymore because you've increased the output buffer, but you're tricking TCP into thinking there's more bandwidth than there really is. And if you do that too much, okay, when you do that too much, you end up with an accordion effect. TCP thinks it has more bandwidth, it lets more packets on the wire. Oops, we don't really have that much bandwidth. Let's contract and start to do the back off. All right? Now, there's another question that I want to answer, and it comes to us from David. And the question is the window size, when increasing the window size, am I also referring to the jumbo frames? And the answer is no. Jumbo frame is how big of a train you're talking about. In my case, it's 1460, the typical Ethernet. If you're using jumbo frames, it's up to 9,000. So basically, you're talking about having a bigger cargo train than a passenger train. Okay? And it's more efficient because you can transfer more people and more efficiently because you have more room to store them onto the train. Now, the reason why I called that question out was this reason. TCP doesn't care anything about packets. TCP has no concept of packets. And you're looking at yourself like, what the hell is he talking about? It's packet analysis. Yes, it is. But in the world of TCP, well, again, this is a fundamental tenet that you have to understand. There is no beginning, there is no end for TCP. Once that socket is open, application gives data to TCP, and TCP transmits until told otherwise. Okay? Because think about it, from the textbooks that we read, from the RFCs that we read, TCP doesn't packetize data. Okay, that's the job of IP. And Ethernet frames it in its Ethernet and electrically puts it onto the wire. So the train analogy, okay, of jumbo frame that I talked about with a bigger freight train than a passenger train is a perfect analogy. When you put packets onto the wire from a TCP perspective, it's like putting passengers onto a train at the train station. TCP doesn't care who gets into what car on the train track. All TCP cares about is how many passengers, how many bytes of data I've transmitted. And God forbid those trains go derailed somewhere, you Xerox copy the passengers and resend them. That's the retransmission and the guaranteed delivery. Okay, so again, yes, we do packet analysis because that's how it manifests itself on the network, but from a TCP perspective, packets don't matter. It's how many bytes of data I've sent. Okay, so hopefully that's clear. So what we're going to do now is we're going to look at Wireshark quickly to talk about this in action. So let's do that. All right. So here I have a packet trace. Okay, and I'm going to walk you through a couple of things that are important and orient you. So clearly, judging by the title here, we can see that this is a slow FTP transfer, okay, or it's a slow application. The fact that it's an FTP or not, honestly, doesn't matter. This can be any application. You'll also note that my Wireshark probably looks very different than what you're used to seeing. Okay? I have all these columns here that are not standard with Wireshark by default. And that's by design. This is where the chapter 2, the mise en place of Wireshark, where to put the columns, how to set this up, comes into play. Okay, so I'm going to forego that for now. Just kind of take it on faith that you'll know how to do this if you attend the second session or watch the video that I have on my YouTube and wireshark.org. Okay, how to set up Wireshark itself. So let's take a look at who's sending, who's transmitting, and how far apart these guys are. So the first question I have that I want you guys to think about is, how do I know how far I am from point A to point B? In this case, the 10-dot server versus the 192.168 client. And the way to do that is, there's two ways actually. Number one, SYN, SYNAC, ACK. That's the handshake. Okay? This is when TCP announces itself to one another saying, I want to open a connection with you. Yes, I'll open the connection with you. Yeah, let's go ahead and talk. That's that SYN, SYNAC, ACK sequence. Here, the 10-dot server is opening up a SYN connection, knocking on the door of 192.168 saying, all right, I'm going from 10 to 192.168.1.1, and then the 192.168 says, okay, I want to knock on your door, and I also acknowledge that you've knocked on my door. And we see the client do that. Okay? And then finally, the third piece of the three-way handshake is that the server says, okay, I agree. I know that you saw mine as well, my SYN. So here's a three-way handshake. And sometimes you hear people erroneously say, when you measure the SYN, SYNAC, you have the round-trip time. And that's absolutely not true. Okay? Just know that you really should measure from SYN to SYNAC to ACK. I'm not going to go into the technical reasons why, but essentially it's because you may not be guaranteed, you may not be capturing on the 10 or 192.168 client. You may be somewhere in the middle. your capture point may be somewhere close to 10 or close to 192.168. You don't really know. Okay? And this is why if you measure SYN, SYNAC, ACK, you can be rest assured that it's a good approximation of the round trip time. There's also another way to do it by timing full-size packets and seeing how fast. That's called a continuous round trip time. That's something that we do at Riverbed using our capture appliances to give you, because you know the round trip time changes, right? It changes because that serialization that I talked about earlier. So let's get on with it. By looking at this timing, some point in time, I see the 10.0 client, I see this packet. Think of this as the Big Bang, okay? When I say Big Bang, I mean this is the creation time. Nothing matters before we saw this packet, okay? All of a sudden, we see this packet. Time is 0. The delta time is a delta between the previous packet and the conversation. Again, my video shows you how to set these up, and it's a very, very critical element of troubleshooting. So at some point, at just beginning of time, we see a 10.0 talking to 192.168, and it's a SYNAC. Within 166 microseconds, you can see here that it's 166 microseconds, 192.168 1.1 sends a SYNAC. There is no application involved here per se because this is all TCP's job, and oftentimes it's even handed off to the network card when you use the TCP offload engine. Okay? So considering that we're seeing a SYNAC, an answer to the knock that the 10.0 server sent to us is 166 milliseconds away, we can reasonably conclude that we're in the same data center, if not at the host, capturing this. Okay? So a SYN was seen, we sent the SYNAC, and then about 35 milliseconds later, almost 36 milliseconds, the server finally said, yep, I'm good to go, let's start transmitting. Okay, hopefully you got all of that. Again, I go over these in my SharkFest sessions. Shout out to Janice for running the SharkFest session because it's an incredible wealth of knowledge. If you're serious about packet analysis, if you're serious about protocol analysis, and you don't attend SharkFest, you're really doing yourself a disservice. Okay? It is an incredible event where people like Jasper, Christians, and all the folks that Janice mentioned are exceptionally good at protocol analysis, and I learn something new every year. Okay? And I've been doing this a long time. So highly recommended. Getting back to the session here. So we know that we're capturing close to 192.168. We know that this is a slow response time. And as we look at this screen, there's something that should jump out at you. And I always preach packet analysis as recognition of your screen. Again, this is going back to the chapter 2, the mise en place, how you lay out your Wireshark, because it's important. And you can immediately see some things that are happening. There's a constant delay of milliseconds, 35 millisecond delta there, 35 millisecond delta there. Okay? And in fact, let's sort by this delta time. I click on delta, and you can see here they're almost all 35.5 milliseconds. And they are all coming from the source of 10.0 going to 192.168. And they have pretty much the common packet size here. Okay? All right, so we have some intelligence. This is not random event. You cannot have this much delta time that's almost exactly the same spread throughout the packet capture. Okay? So we're on to something here. These 35 millisecond delays are killing us. So let's see that visually. How do we see this visually? Well, all you have to do is use one of the favorite charts of mine, and that is TCP Stevens graph. So we'll go to Statistics, Tcp Stream Graph, and let's look at Stevens graph here. And what it does is it charts. Let me bring it to my screen that I'm sharing. Here it is. And the idea here is that the steeper the slope, the better the throughput. TCP Stevens graph is nothing more than charting how many bytes I've sent out onto the network over a period of time. Okay? And how you send data onto the wire is measured in sequence numbers. Don't get hung up on sequence numbers. All it is how many bytes have I transferred over time? The more you transfer over time, or the faster you transfer over time, meaning the steeper the slope, the better it is. And on first glance, this looks good. Okay? And again, this is touching on one of the chapters, that false confidence. You look at this graph, nice and steady, looks solid, 45-degree angle. Could be better, yeah, sure, but I'll take it. But devil's in the detail. Let's zoom in. So I'm going to left-click and zoom in here. And now we're starting to see a moment of, that's interesting. Let's zoom in a little bit more. Okay, very, very interesting. Now let's zoom in a little bit more for clarity. And what do we see here? Look at those dots on the screen. There are repeating patterns of 6 dots, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, okay? And it's about how far apart are they? 5.6, 5.65, 5.68, etc. Okay, it's actually about 35 milliseconds. This is a delay that we saw. What's happening in this application is the application itself is doling out 6 packetized data, waiting 35 milliseconds before doling out the next spoonful. Okay? Even though TCP has the ability to transfer this as fast as you want, assuming the window size is big enough, the application is unwilling to give you that data that you need to transfer. Another way of putting this is you have a 50,000-gallon water tank that you need to send to the other side. You plumb it with a massive pipe, okay? I don't know, a foot, a meter, half a meter diameter pipe, doesn't matter. That's the bandwidth. Unfortunately for you, the application wants to give you data in one bucket size at a time. And each bucket size compromise is made up of these 6 data points. So notice what happens when I click on this dot here. In the background, you can see that packet number 1386 was highlighted. And then I click over here on the last of the packet train there, and you can see it goes to 1394, packet number 1394. So let's click on here again, and that's 13. And we can see it's 1386 to 1395, I believe. That's what makes up the 6 packets. Okay? So you got this massive pipe, a lot of water to transfer, but unfortunately the application is unwilling to give you more than 1 bucket at a time. So how do we prove that? So it looks logical. It fits the hypotheses, this transfer diagram of 6 packetized data, waiting, 6 packetized. But how do we prove that? Okay, let's see what it looks like from a packet trace standpoint. Here we have the delta that we saw, the 35 milliseconds. Okay. And let me scroll down just a little bit so we have more. And you can see that I'm transmitting here, 1446, 1382. I'm transmitting here, okay, transmitting here, and transmitting here. Okay? And then there's a long delay of 35 milliseconds. So these packets that I just highlighted are the 6 packets that make up that burst of packet train. And what do we see in common here? What do we see from delta to delta, meaning from 1386 to here? What do you notice? There are a couple things that should jump out at you. Number one, the amount of data being transferred is remarkably the same, the pattern. Okay? 1456, 1456. Okay? And this is with IP and header, so it's 1390 from a TCP standpoint. So let's look at it from a TCP data standpoint, not with the IP and TCP header overhead. So I'm transmitting 1390, 1390, and 1316. And then I repeat that pattern again and again. 1390, 1390, and back to 1316. Okay? There's something else that's interesting. So let me go back to here. So here's that 1390, 1390, oops, sorry, and 1316. Okay? 1390, 1390, and 1316. What's interesting here is that on the right-hand side, we actually see push bit here and push bit here. Okay? In between from this point here going down to this point here. Okay? We see a repeating pattern. By the way, for those of you that are curious, if you add up that number, 1390, 1390, let me do that for you so you can see it for yourselves. So what do we have? We have two 1390s and a 1316. Oops. Give me 1 second. Let me go back to Wireshark here. Okay, so 1390, we had two of those. And then we had 1316. We add that up, 4096. Here's a tip for you. When you're doing troubleshooting and packet analysis, look out for these numbers that end exactly in the boundary of 1024. Because more often than not, that's the application, because every developer counts and thinks 1K is 1024. Every network engineer thinks 1K is 1000. Okay? So these are good numbers because this is telling us that the application is getting involved. Another way to know that is that you notice there's a push bit set. This is significant. This is like the application saying, hey, here's a bucket of water. When you're done, I'll give you the next bucket. Okay, does that make sense? So the push to push oftentimes denotes how much data is in a bucket, and the application is willing to give us in a bucket's worth of data. And we saw that. But some of you should have, as you were paying attention, and maybe some with more experience, said, Hansang, wait a minute, this makes no sense. In our Stevens diagram, let's go back to our Stevens diagram, we saw how many dots lining up. Anybody remember? Let me bring it to the screen. Zoom in a little bit more. 6. Okay? We see 6. And I just showed you the 1390, 1390, 1316 repeating twice. I also said the application, when they put the push bit on, that's like the application giving you the bucket size. In this case, the application is willing to give you 2 buckets worth of data, serially. Okay, so think of this as 2 guys sending the bucket worth of data, that's 4096, another 4096, sits and waits until it gets an acknowledgement, and then you see it again. Okay, I showed you that graphically. So while you can do this in Wireshark, and I've just done it for you, it does take some analysis, it does take some experience, and it does take some understanding of how protocols work. I'm going to now show you a slightly different version from a product that we call Transaction Expert. Some of you know it as IT Guru, some of you know it as ACE, some of you know it as ACE Analyst, I think, maybe. I wanted to show it to you because visually, this is what it looks like. Okay, it's the same trace file, and you can see from here in the Transaction Analyzer that when you open this, the application is saying not the 6 packets at a time, but 4096. Here's the application sending 4096 bytes worth of data consistently. Okay? And you can see here over time, this is what's causing, this is what's happening. 4096, 4096, 4096, 4096. But we saw 6 dots, not 3 dots. So let's zoom in from a, think of this as a TCP bounce diagram. Let's zoom in a little bit. And now let's zoom in a little bit more. And we can clearly see that when I highlight one of these blue bars, we can see the 6 packetized data that we saw. Okay, 1390, 1390, 1316, 1390, 1390, 1316. However, by hovering over this white bar here, you can see, let me do this one here so it doesn't get chopped off from the screen. You can see that there's a dependency from the previous blue bar to the next blue bar, and you wasted 35 milliseconds of application processing delay. Okay? It's an application processing delay because you got 2 buckets worth of data, 4096, 4096, and then the application said, I'm not going to give you any more. You may have the biggest pipe in the world. You may have the biggest warehouse with a shelf space in the world, but I, the application, will not give you more than 2 chunks of 4096. When you're done with 4096 and the 4096, 2 chunks of it, come back and I'll give you more. And every time that happens, you waste 35 milliseconds of round-trip time. Clearly, this is a poorly designed application. And although I said that TCP window size problems are the easiest to solve, in this case, solving it with TCP window size will not work. Because how many bytes are outstanding at any given time? 4096 times 2. Okay? So, hopefully, that was introduction to the topics that I want to cover. And what I realized is it's going to take a lot more than 8 sessions to cover 8 chapters. Okay? So this is a taste of what's to come. And what I want to do now is turn it over some more Q&A, and I'll have a better sizing in terms of how much data we can present. Okay? So I'll probably in the future spend 10 minutes on PowerPoint theory, etc., and the rest of the time on packet analysis. Okay, so Janice, you want to take over the reins, and
Yeah,
I think
thank
you had
you.
some
Thank you,
couple things
Hansang.
that you wanted to announce. And
Well, yes, thanks. So, again, thanks everybody for your time and attention. Hansang's a great presenter. Thank you, Hansang. And he did give you if you haven't been to SharkFest, he did give you a taste of the quality of the education you get at SharkFest. We assemble an amazing team of veteran presenters, like Hansang, over the course of 3 days, in 3 tracks that are beginner, intermediate, and advanced and developer specified. So you can choose your track, you can go between tracks, you can do whatever you want. Again, in the email that will be sent within a few days to all registrants, you'll have information on not only the location of this recorded event, but also you'll have information on how to find out more about SharkFest. And again, there are 2 SharkFests this year. The one you're going to be finding out about and pointed to is the one that's happening at the Computer History Museum, June 13th through the 16th in Mountain View, California. We will have a website, a new website for the first SharkFest in Europe that will be held in the Netherlands, October 17th through the 19th. And we'll be sending out email on that one after the website launches in March. So both events, again, are as far as the attendees of the last 8 of these are concerned, are worthwhile events. So if you are interested in an immersive sort of Wireshark training experience, then please do check out SharkFest. And watch for the email, with information on the location of Hansang's recording for this live event, and a little bit more information. And again, registration for the next 2 events in this series, May 12th and August 18th, you'll be receiving information on how to register for those events a few weeks before they occur. So if you want to mark your calendars now, May 12th, again in this same time slot, 10 to 11 Pacific, whatever it is at that point, Standard Time, Daylight Time, I can never remember. And August 18th again, same time slot, 10 to 11 a.m. PST,
Great.
PDT. Okay?
Thank you, Janice.
All right.
Thank you. So what I'm going to do now is try to answer as many questions as possible. Some of these I can answer very, very quickly. And I know we're a little bit over time, so those of you that can hang on, by all means, hang on a few more minutes. Those of you who can't, watch the replay, and you can. Some of these questions are very, very interesting. Okay, number one, sounds like a sliding window. There's some form of continuous flow, not a full stop. Yes, that's true, but the important factors here to have learned is that the push bit almost always denotes when an application wants to stop transmitting, regardless of what TCP wants to do. Okay, so it's not so much a sliding window per se, it's the application is dictating how much it wants to dole out. And your job is to figure out what is that bucket size. Okay, because the bigger the bucket size, obviously the faster the throughput, assuming you have bandwidth and TCP window size. What about MTU, maximum segment size on network equipment? So Corey, the answer to this is that there was an upcoming session further down that talks about a significant issue that caused all kinds of havoc, and it had to do with MTU. So I'll table that for a later session and use that as a teaser for the next one, next couple of sessions. TCP Frozen Window. No, this is not TCP Frozen Window, because when TCP Frozen Window means that, for example, when it hits the 0, that's a use case where, you know, again, that's an easy one because TCP is saying, please shut up. Okay, the receiver is saying TCP window size of 0, you know, the idea that TCP window going down, getting smaller and smaller is a problem, that's a misnomer. You want that TCP window size to go down because that means you're putting more bytes onto the wire, and as long as it doesn't hit 0, and as long as the TCP window size recovers, and that means you're doing a very efficient job, okay? And how do you more buffers and routers give you more bandwidth? Because think about having, what do buffers do? Buffers artificially elongate the pipe. Okay, if you have a pipe, it can only carry so much data, so much water in a given time. What buffers do is you're putting the S-curves and these curly curves within that pipe, and you no longer have a straight pipe. So essentially what you've done is you've elongated that pipe, which means you have more, essentially more data that can be outstanding because everybody's queuing it up. Okay? Does Windows auto-tuning window really work? Yeah, there were some rough patches in the beginning. What you really have to worry about, David, now is that CIFS transfer, and Jaspert showed this in one of the SharkFest sessions, CIFS, the most modern version of CIFS, okay, can sometimes bring an onslaught of data. It crushes switches and routers, and there's going to be congestion, packet drops, and TCP throttles down. Okay, so that's the case of too much of a good thing. And in the future, I plan to have people like Saki and Jaspers of the world come join me to present these corner cases that are very interesting. Okay, and the next one is the anything to do with SharkFest. Let Janice know. She's the caregiver. And Jeffrey, you had a question about window size. So I went back to the live window sharing, and you can see here that I'm using 65528 on the server side, the 10 dot, and 192.168 starts at 3674. Okay, 36574. So clearly, we're not being gated by TCP window size. And by the way, if we were being gated by TCP window size, what would we have seen? TCP window size of 0. Okay. So there was a question here, Christopher. You are an eagle-eyed viewer because he's asking me, why are you using 1.10 when there are newer versions of Wireshark? And it goes, there's two reasons. Number one, if you see at the title bar, it says Wireshark 1.10.12 RVBD. We have some dissectors that we use internally, and so while that's being caught up, I'm still on 1.10 for that purpose. No other reason than that, no big conspiracy. So if you subscribe to my channel, every time I post a new video, you'll know about it. And so that's the best way I can tell you, other than the 3 seminars that Janice went over. So is there a way to inform the developer to increase buffer in the application? The answer is yes. And in the future versions, you will see how both in JDBC, ODBC, and Oracle TNS Listener, you can modify that because that's an easy, it's not a code change, it's just a tuning parameter when you make a connection in the world of Oracle Sybase and ODBCs. And I'll show you exactly where to make those, essentially what you're doing is making the buffer size or the bucket size bigger. And sometimes that is the only way you can fix the application is via an application rewrite. Okay, that doesn't come to happen often, but when it does, it looks, you can get mind-boggling performance. All right, so I'm going to spend a few more minutes picking up, and thank you for all you well-wishers out there. I appreciate it. And is this an example of a deep explanation of how TCP works? Yes and no. When sometimes in the Shark Fest that's coming up, I'll probably spend entire hour and 15 minutes on just a few lines of a trace, okay? Because that's, when I say deep dive, that's the level that you can go in, and I can spend 20 rows of packet data on an hour and 15 minutes because that's how difficult or interesting it can get, okay? And for those of you that got this notification via Riverbed mailing, make sure you don't put us on any kind of filter, and that'd be good. And what is the title of my book? Remember, I stopped, and I wanted, it's The Art of Packet Analysis was going to be the title, and now I'm going to just publish it on YouTube, so don't forget that. And how do you adjust the window size? On the router, you don't. So the routers have no concept of window size. All they have are buffers. Okay, how big that buffer is manufacturer and ASIC dependent. So I will tell you, and this goes to foreshadowing of my large enterprise, when you work in a large enterprise, sometimes you have access to information that, lay people or, the folks may not be able to have. And that is sometimes it comes down to ASIC and FPGA design, and sometimes you need to know that level of detail to troubleshoot. And in a future session, I'll talk about how we were able to find an issue with a buffer size that was built into the ASIC itself. All right. And TCP flag as a column, absolutely. Anything that you see in Wireshark, you can pretty much right-click and apply as a column. That's covered in my mise en place, the how to set up Wireshark properly to do that. And the link to the recording of the session will go out as a follow-up email, so no need to worry about it. And how can devices in the middle impact window size? I hit upon this earlier. So it's not that the window size is changing, it's how much it can buffer, which can force TCP to think there's more bandwidth than there is, okay? And that leads to the sawtooth throughput graph that you see where TCP goes up, and it crashes and goes up and crashes and it goes up, and and there are a couple different ways to address it. Chris, and I believe with British Columbia, says there's QoS and congestion avoidance, and the answer is absolutely. QoS can help, and there's a reason why QoS tail drops or does random early detected drops, so that you don't artificially impact TCP. And again, these are all questions. I'm firing off the answers as quickly as possible, but these are all things that you should listen and Google and search for, right? Dropping 2 packets in the same window size, detrimental. It drains the pipe. What does it mean to drain the pipe? Google it. Okay? We now live in a world where Google can answer pretty much anything. So with that, we're 10 minutes over. There's still a lot of questions. I'll try to get to them as best I can. And I believe the live session on the On24 is going to go on for a little bit more. So I'll try to answer via email. What's going to happen is I'm going to get a recording or printout of all these questions, and I will do my best to reply to you individually via email to answer them. Okay? All right. Ladies and gentlemen, good evening, good night, good morning, good afternoon, wherever you are. Thank you for joining. It was nice to see some of the familiar names in the attendee session. And as Janice mentioned, look out for the other 2 sessions. Look out for my YouTube channel because more and more content will be published there. Okay, with that, thank you very much, and I'll sign off.